ChatGPT is telling me that there's millions of black holes in our galaxy.
And also estimate how big.
I guess it kind of makes sense if if you remember that diagram that we talked about where the Chandrasekhar limit was discussed, where essentially if you have more than a few solar masses, the ultimate fate of the star under the gaseous model has to be a black hole, essentially, because you compress those white dwarfs as they run out of that reverse pressure, then nothing's holding them from collapsing, right? So they're treated as ideal gases. So eventually they reach this space where they have no diameter left, and so that seems to be a very common part of the normal story for gaseous stars and their fate. Yeah, that is astounding. Millions of them. So there you go.
The black hole at the center of our galaxy is called Sagittarius A.
That's right. Supermassive black hole. So we'll talk a little bit about those too. That's kind of building out the story of these quasars, which I mentioned, and I realized we hadn't dealt with them yet. So we're going to spend some time with quasars today and make sense of this. But essentially, a lot of these galaxies, especially the ones that we look at that are far away, seem to have these central features that are really, really bright. They're so bright that the easiest way to explain how something could be so energetic is something like a black hole. There are some alternatives as well too, and it has to do. There's different alternatives. There's alternatives that involve, well, maybe they're not as far away as we think, and that's why they're so bright. And there's alternatives that suggest there's other ways, especially magnetic ways, of making these powerful jets happen, which is kind of interesting. So I'll play with those by the end of the class today. This is good though. What else, guys? Yes. Yeah. So the monolithic collapse model is very similar. It's almost exactly the same as the standard formation model for stars and for solar systems as well. It's like big balls of stuff swirling around, collapse on one another. I think that it is. I think that in some sense, this is not a theory that will completely disappear ever. I think it's just a matter of what contribution does gravity make to it and what contribution does chemistry make to it, I think, is what the real argument is going to come down to. So, for many, many years, actually, even when I first started teaching this class only a few years ago, gravity was assumed to be the main player in that story. The problem is most of these clouds that we witness aren't gravitationally bound. They're just kind of diffusing off into the distance. And so there tends to be, over the last few years, there's introduction of more and more processes that could concentrate matter that isn't just depending on gravity, which is reassuring because I found it even 3 years ago very disturbing that this idea that gases would somehow just by themselves spontaneously collapse on themselves. You take a balloon out in space and pop it, like that's not going to happen. And I don't see how having a huge balloon is going to really change things. Gases, especially ideal gases, they diffuse indefinitely. So, once you start introducing chemical processes, right, you introduce basic condensation reactions, you can start to glom together little pockets of matter, right? It's really cold. And remember how we talked about it's almost absolute zero inside of these clouds. So, think about, you're seeing your breath on a cold day, that kind of thing, right? Condensation reactions, I think probably drive a lot of this. And I would imagine that that a galaxy's formation isn't so different from a star's formation. It's just a little more complex. It's like talking about a storm versus a single raindrop, something like that. But yeah, good question. What else, folks? Anything? All right. All right. All right. I'm gonna come around. I'm really enjoying this iPad now. And I forgot my microphone, so we'll use this one. All right. So yeah, I want to talk about these quasar things because they tend to make up the majority of the situations where we're talking about really high redshifts. So things that we can see that are far away. if you think about it, what are we going to see that's far away? Things that are brightest, right? And these are by far and away the brightest objects that we can see at distance, right? They're these things called quasars. So it's like, what is a quasar exactly? Quasars are really, it's a special case of what's called an active galactic nuclei, which is really just to say there's something really powerful and bright and energetic happening at the center of galaxies. And these quasars are essentially these massive confluences of material, and they tend to have these polarized jets which stream material and radiation out in either direction, kind of similar to a neutron star, or really even a new star that's forming. They kind of do the same polarization where they spray this material out. So something really interesting seems to be happening at the center of many galaxies. It's not happening at the center of our galaxy, which is kind of interesting, and I'll circle back to that because it looks like it might have happened in the past. So it might be a particular stage in the evolution of a galaxy. It kind of adds to the fuel for people who think that galaxies only formed once, right? So the general story, the universe formed 13.8 billion years ago. There hasn't been enough time for galaxies to form, fall apart, form again. And part of the what would proceed from that assumption would be that if we see really far away a lot of these quasars, a lot of these really active galactic nuclei, well, really far away things point to really early times in the universe, right? And so the idea is that maybe they're kind of an evolutionary step, like sort of like when stars form, we see these huge jets, right, coming out of the center of these T Tauri stars. We showed some pictures of that back in the day with the HH objects and everything like that. Similar kind of thing. People think perhaps the quasar or the active galactic nuclei is a moment in the formation of the galaxy itself. And that may be the case. There's some other possibilities we can check out as well. So, but whatever the heck is going on, it's very, very bright, and they tend to be very, very red too, which is interesting and requires an explanation. So I'm talking about quasars, talk generally about AGN, active galactic nuclei, and then we'll play with the mechanisms. And then I'm going to try to actually basically squeeze in 2 classes worth of stuff since we're behind, and I want to have plenty of time for the CMB on Tuesday, and and really to put a bow on the Big Bang at the end. So this name quasar started off as shorthand for quasi-stellar radio sources. So they were essentially discovered right after World War II when people really started playing with radio telescopes for the first time and being able to assign locations for these radio sources. And they discovered that there was these huge radio sources coming from the same places as these really faint blue stars. And nobody knew of anything in our galaxy that could do that, essentially. So this was, again, very early, really right after people even started considering that there were other galaxies at all. And very quickly, people began to consider that what they were looking at was something on the galactic scale instead of something locally, right? Something very, very big and far away. But what was really perplexing is at the same time, people started noticing these enormous redshifts. And when I say there was enormous redshifts, the first one that was discovered had a recession velocity from the redshift, so it was moving away at something like 15% the speed of light. Now that's really, really fast. That's something like 45,000 kilometers per second, which is quite a bit faster than my car goes. I don't know about you. And the more that they studied these things, the more that they found these ridiculously high recession velocities for these things, eventually reaching up to speeds of 95% the speed of light. So that's really interesting. And this actually fed quite heavily into the expanding universe idea, because people were thinking, how in the world could this possibly be happening, right? These recession velocities are almost impossible. Like, I guess it's worth kind of mentioning, like, why is well, first of all, the speed of light seems to be the limit at which the fastest that anything can move in the universe. And the idea that things could be moving at 95% the speed of light kind of defied imagination, and this, in some sense, reinforced the idea that the space itself was expanding, because nobody could imagine how something could move at 95% the speed of light. why is it so hard to go at the speed of light? Why is there even a speed limit on things in the universe? Anybody? You guys ever think about this? What do you think, Levin? I know you think about this kind of stuff. Anybody? It's kind of weird, right? You would think that, if you just pushed something fast enough, it would maybe go faster. Well, it's kind of interesting. I mean, I guess we could back it up and be like, um, any material, any sort of deformation of a material has a speed limit. So let's say if I like pound my hand on the desk right now, I'm actually deforming the material a little bit, but it's pretty rigid. So what's going to happen is there's going to be a wave of deformation that travels down the length of the table. So if I put a little measurement device, like a little microphone contact mic on the end over here, I can actually measure the speed at which that deformation traveled in the material, that wave of deformation. And you can do this in gases, you can do it in solids. In gases, it would we would refer to it as the speed of sound, really, right? You're deforming the air. And it's kind of limited by how fast those air molecules can get out of the way, really, is what it comes down to. So have you guys you ever seen like these like fighter jets breaking the sound barrier, the sonic boom thing before? Kind of crazy, right? So they're moving so fast that the air can't even deform and get out of the way. They're literally ripping a hole in the air. And so oftentimes you see the plane go by before the sound will reach you like a few seconds later, right? Well, boom. And so you get that crack. It's almost like a thunder, the way that thunder does the same thing. So anyways, my point is that in any material, there's a speed limit. And it has to do with how fast the subunits can get out of the way, how fast it can be deformed. So when I look at something like the speed of light, my immediate mind goes to, well, that's the indicator of the deformability of whatever that wave is traveling through. And I've talked to you guys a bit about how we abandoned the search for the mediator of light, right? Most people, even scientists, treat light like it's kind of these little magic bullets flying around, or maybe it's waves of electromagnetism when that's convenient, but it's still one of the most outstanding paradoxes in all of physics. How the heck can something like light be particulate in some cases and wave-like at the same time? Is there a medium for it? People kind of gave up on that. Now, does anybody remember all the way back to the beginning why people gave up on the search for the mediator of light and gravity for that matter? Yeah.
Stop, you go crazy, guys.
I mean, I think that's sort of the emotional background for it. There was some experiments where they tried to detect it. Does anybody remember those? It's okay. So we talked about the Michelson-Morley experiment as being the most famous version of this. But essentially what people thought was, they thought this mediator, this medium, let's say, you guys know what a medium is? It's just a substance upon which something plays out, right? Like we have media, right, which is like YouTube and stuff, but that's also like sort of a substrate upon which movies play out, right? The same thing in physics, same thing in biology. If you grow cells in a culture, you grow it on media. And in this case, what they imagined, the assumption going into the experiments was that, hey, there's atoms and they send signals to each other through some sort of external medium that's separate from the atoms. And if that is the case, we should be able to detect it because there should be a little bit of a lag. As the Earth moves in its orbit around the solar system, there's going to be a little bit of a lag where it's going to sort of, miss the detector, let's say, by a little bit when we try to catch these photons, something like that. And they couldn't detect a lag like that. They didn't detect this, what they called the ether drift. And so hundreds of different people were trying these kind of ether drift experiments. Most famous was Michelson-Morley. And the conclusion was, it's not there. There's no drift, therefore there's no medium at all for light and gravity. Which is interesting because one of the things that happens in science is that oftentimes when a bunch of people try to do an experiment and it doesn't work out, they throw their hands up and nobody tries again ever. And so that was 125 years ago, essentially, 130 years ago, that people last really revisited this idea. The way I'm looking at it is that perhaps the assumption that the medium should be separate from the atoms themselves was the culprit in the situation. And so if the atoms themselves do have this extended furry structure, like I suspect they do, then the transmission of waves in their surface is really quite simple to explain. And there's no way you're going to detect a separate substance from the atoms themselves, right? So anyways, all this is to say that the reason there's a speed limit for light probably has to do with the material character of those atoms and their outer extended shells as well. So the atoms can only be deformed at a certain rate, which owes to the little subunits that they're made out of, whatever the heck that is. That sort of fiber of their existence is only able to get pushed out of the way at a certain limit. And light seems to be it travels in the most thin, rarefied portions of that material. So I guess it's worth also pointing out to you guys that how do you have a really fast speed in a material? So how could I make the fastest wave in a material? The material would have to be extremely stiff, and it would have to be really, really rarefied. So really, the subunits would have to be kind of far away from each other, essentially. That's how you maximize the speed of travel. So it sounds to me like perfectly compatible with the idea that the atom has this rarefied outer structure, and that the surface, that the atomic structure is really stiff also because it's a really fast wave. So I think this is interesting because what we're talking about is something where the atoms themselves or the light is moving at a really, really, really fast speed, almost approaching the speed of light. And it's very difficult for people to comprehend because, well, we can't see how atoms could be accelerated even close to that speed here in a laboratory on Earth. So it's very perplexing to everybody. And again, it helped them build out the idea that the space itself must be expanding because they couldn't possibly be speeding away that fast on their own. So these are some Hubble images of these quasars. One of the little bright stars in the middle there is actually in our galaxy, but the other one's a quasar 9 billion light years away. And it's being outshone by that. Our own star is being outshone by that quasar, which is kind of extraordinary. So originally, none of the quasar spectra, they all showed redshifts. None of them showed any kind of blue shifts. And so again, that's slotted into the model. We're going to talk about some exceptions to that in a second, which is sort of gives us food for thought about reconsidering this interpretation. All right. So, by the way, concerning the stiffness of the medium itself, there was a series of papers that came out of Princeton, or actually one paper came out of Princeton that examined if space-time was an actual medium, how stiff would it be? And they can do that essentially trying to gauge if there's something holding the sun to the Earth, how much material tension must it be able to withstand? And the answer is something incredible. It's like thousands, maybe millions of times that of steel, an unbelievable stiffness, which is quite fascinating. But it's not inconceivable for fine structures, actually. Actually, spider webs have incredible stiffness to them, considering how little they are. Their stiffness, if I recall correctly, approaches that of steel, which is incredible. Of course, it's a very small amount of material, so you can break it with your hand. But if you were to make the web out of steel, I think the spider web would contend with it, which is fascinating because it's a flexible polymer. Okay, so, all right. So enter, I brought up this guy last time. He was one of Hubble's graduate students, this guy named Halton Arp. Now, Arp made his career out of assembling this atlas of peculiar galaxies, where he showed that many of these quasars that had otherwise really high redshifts seemed to be directly attached to objects in nearby galaxies that had really low, if any, redshift at all, sometimes even blue shifts, which was his first sign that perhaps the quasars weren't as far away as they were being suspected to be based on the redshift. Remember, guys, when we talked about building that distance ladder out, we said you can see directly through parallax nearby stars. And then we can use the characteristics of some of those nearby stars, like Cephids, these pulsating stars, to be able to say, oh, there's a Cepheid really far away. It's dimmer by this much, so it must be this far away. So we get these standard candles at some point. We can't use parallax. And then at some point, we can't even use Cepheids, so we got to use supernovas and their light curves to see how far away things are. At some point, that doesn't even work anymore, and so we just depend on redshift to tell us how far things are away. The problem with that, of course, comes down to the fact that perhaps there's other ways of getting redshift, not even the tired light that we talked about. Perhaps objects have intrinsic redshift based on whatever strange physical or chemical processes are happening. So he essentially noted that, even in cases where these active galactic nuclei were pointed directly at us, in other words, that the jet should be flying directly towards us, there's cases of high redshift emitting from these objects, which didn't make any sense to him at all, because if things are being ejected from the center, they should actually be blue shifted towards us, and it didn't seem to be the case. So he hypothesized that there was something about these jets, something about these it's a hard word to say, active galactic nuclei, let's say AGN, something about these AGN that produced an intrinsic redshift, something inherent to what was happening inside of them, although he never made it as far as actually figuring out what that was. There's a couple of recent papers to that end that are kind of interesting as well. Everything from people finding these bridges between low redshift galaxies and high redshift galaxies. In other words, there was material kind of strewn between them that suggested that they were actually linked up to each other, but they had a completely different redshift in their AGN spectra, which is really perplexing. Another paper, similarly, these guys actually, even weirder, they found that there was an inherent blue shift inside of the spectra of some of these redshifted galaxies. So parts of them would be highly redshifted, but other parts of them would be highly blue shifted. All this is really just to open your eyes up to the fact that there might be more happening here than the simple story that redshift means recession and blue shift means whatever the opposite of recession is, advancement. I don't know if you guys can think of anything better. There might be something else going on there, which is quite interesting. The other thing that's kind of interesting is that all of this quasar luminosity seems to be coming from a tiny little space. So basically what you can do is, if you're looking at something that's really far away, you look at the light that's coming from it, and the light should be kind of spread out. So if a change happens on one side of the galaxy, it should take longer for it to get to us. Makes sense, right? Because light has to travel across all these, tens, maybe, how big did we decide that I can never remember these numbers, they get out of control. The size, can somebody just Google the light year size of the Milky Way galaxy? That would be interesting. Well, anyways, the light has to travel completely across that, right? And when they do that computation for the size of these quasars, they end up with regions that are really tiny, something like on the order of light months instead of light years, which is really crazy. So, Pluto, for instance, takes something like 5 or 6 hours for the light to get to us, right? So you can imagine that these objects, if they're only a matter of light days or a light month across, they're really tiny region from which all this energy is being emitted, which is really, really interesting too. Did anybody look it up? 100,000 light years across, right? So it should take a really long time for the different pieces of that signal to reach us. And in fact, it only takes, some light days for that whole signal trace to be recorded. So there's something really interesting happening. We're not talking about the whole galaxy. We're talking about a tiny little piece of it, not that much bigger than a couple of solar systems across, which is really, really far out. All right. Here's another picture of one of those jets, and some different wavelengths. Okay, so the standard problem is that these things are tiny. There's an unbelievable amount of energy and light as a result of that being emitted from a tiny little place. And, as history unfolded, the only thing that people could think of in the mainstream explanation space was that there had to be black holes that were enormous. They call them supermassive black holes. We're talking about just whole just dozens of massive stars worth of material collapsed and polarizing all of this material at the center of these galaxies. So that explanation obviously didn't appear until black holes became kind of part of the standard canon. So another explanation people entertained over the years was this idea of superstars. So we talked about what could be happening at the center of our own galaxy. What could be causing all of this mass. And the superstar idea has actually been all right? Okay. The superstar thing has been entertained seriously over the years, but the problem is people figure that if there's a bunch of huge stars at the center of these galaxies, that they would be kind of colliding into each other. And then if they're colliding with one another, then they're going to merge. And if they merge, well, because they're gaseous stars, they're going to collapse and make a black hole anyway. So it's kind of a non-starter of an idea. Liquid stars, you don't end up with that same problem, of course, because liquids never collapse upon themselves. All right, so this is a hypothetical reconstruction of our own galaxy. So in our own galaxy, we don't see huge jets streaming out of the center of our galaxy, but we do see these kind of interesting bubbles from our galactic center. These are just bubbles of ionized gas, and they emit really high energy photons, these gamma rays. So the theory, like I was kind of alluding to earlier, is that perhaps our galaxy, perhaps this is kind of the cooling off of these jets. Perhaps our galaxy has been through this active nuclei stage at some point, and it is no longer there anymore. Maybe so. Look at those things, though. They're enormous. What is that? Like 50,000 light years in either direction. Or I guess, completely spanning it. Unbelievable. All right, so another set of possibilities for these AGN is magnetic in nature, which I find rather intriguing. And I talked to some people about this. I think I mentioned to you guys last time that the galactic magnetism is very difficult to parse because, in this picture with this magnetic field here, it's a very nice, neat magnetic field like you would expect around kind of a bar magnet or a solenoid, something very simple. Unfortunately, the actual galactic magnetic fields are a complete mess. So they're often curling around the different arms in different directions. There's often different sheaths of magnetic activity. So you might have a magnetic field going one way, and then a few at a different depth, you would have a different magnetic polarity. And so they're kind of layered like onions and very complicated and difficult to study. The only way you can actually even study magnetism at a distance is by looking at how light gets polarized. And so you're kind of making these leaps of faith at each direction. Now, the authors of this paper actually provide some possibility set for us for how this could happen. So if you guys think about, you guys are probably too young for cathode ray TVs. You guys remember those big tube TVs that or the computers that would sit on the desk? Anybody see? You guys are too young for you've seen it? All right. You guys know about these cathode ray TVs? You've probably seen them in movies at least, computers used to not be flat. Like they used to have these huge, chunky, hefty glass tubes inside of them. And the way that would work is there was some ionized gas inside of these tubes, and you would use magnets to kind of focus that beam, they would call it like an electron beam, on the back of the screen, essentially, and you would just go line by line. It would go at a very fast rate, and it would generate this fluorescence, this phosphorescent image on the back, right? So this is why all those computers were just one color usually. In the early days, they were just green, glowing. But the interesting thing is what you do is you basically use a magnetic field to focus a column of ionized gas, right? They call this electron beams, but it's ultimately this ionized gas that's being focused. So could something similarly be happening at the center of galaxies as well? If you actually do have a magnetic constriction like this, could you have some super energetic process at the center that's actually focusing all of that, let's say, dissipating material away and accelerating it very much the way that these cathode ray tubes did in TVs? I think that's a pretty intriguing idea. There's also an argument called MECOs, MECO, which is magnetospheric eternally collapsing objects. And this is a more mainstream argument against the supermassive black holes, where they actually suggest that as all this material is getting heated up and energized and emitting these jets, that it induces its own magnetic fields, which would resist the gravitational collapse necessary to even form black holes in the first place. So they're actually supported by magnetism rather than collapsing under gravity. That's an interesting idea too. Halton Arp, at the end of his career, also suggested that perhaps perhaps instead of these quasars being receding really fast, that there was some sort of lensing event happening, which led to this appearance of redshifts as well. So you guys remember we talked about the different possibilities for light being bent at some point. And we talked about, under general relativity, the path of the space would actually be different, the light would bend. The other possibility being that these really energetic plasma atmospheres of the stars is somehow lensing, just like a different refractive media, like when you try to like grab a fish in the water and you miss because the light is bent inside of the medium. Something like that could be happening. And so Halton Arp was suggesting that perhaps as a foreground galaxy passes or a star passes in the path of that light from these AGN, that the sort of warping, the lensing of that really rare, high ionized atmosphere of that galaxy, that star, led to this appearance of this redshift that might actually have had nothing to do with its recession in the first place. So anyways, if you guys want to learn more about these magnetic fields and galaxies, there's a cool textbook out there. At least people who are listening to this video at home might want to check this out. It's called Cosmic Magnetic Fields by Keppins and Goldblode and Porth, which is interesting because it addresses AGNs from a completely different perspective than as these super recessional objects. I also did a cool podcast. I mentioned this last time. I just want to show you guys. This was podcast number 196, where we met with the guy who studies these magnetic fields at Stanford, and he will talk your ear off about everything they know. But what's really interesting is I remember him, we did this podcast like 2 years ago, and I remember him saying there was only like, a dozen people or so in the whole planet who are studying galactic magnetic fields. So it's a really, really brand new science. And I wouldn't expect that it would have made it into the textbooks by now. So, what do I want to say about this? There's a really interesting principle that I think we should probably work towards introducing, which is that all of the models that we build for things assume that whatever happens in one part of the universe is more or less going to be happening in another part of the universe. This is called the cosmological principle. It's like things that happen in our laboratory should essentially be the same things that are happening in a laboratory on the other side of the universe. And it's interesting because the question becomes, if that's the case, why are things so very, very different at these distances? In some sense, this is the thorn to a lot of this cosmology, because if we start assuming that things at the beginning of time were different, then we've sort of violated this isotropic, homogeneous roadmap for how the universe should operate. In other words, physics should kind of be the same everywhere. And we're going to look at some really interesting pieces of evidence for why that doesn't really seem to be a useful principle in the long run, even though everything kind of revolves around it being the case. I want to talk about some extraordinary large-scale structures here in a second. All right, so let's do that. So what's really interesting is that if you accept this idea that the only way that we get these really big redshift galaxies at a distance is that they're flying away from us, and they're not flying away from us because they're being propelled, but they're being flying away from us because the space itself is expanding. Turns out that there's no visible explanation for how in the world that stuff could be moving away so fast, right? So if we try to pin it on gravity or something, then you need some sort of matter outside of that matter to be pulling it apart, right? And so the standard cosmology that we'll talk about, the Big Bang cosmology, is given a name. It's called lambda CDM. The letter lambda stands for the cosmological constant, which is basically talking about the rate of expansion at different epochs. The CDM stands for cold dark matter. The reason for that being that the only way to explain how these structures hold together over time while simultaneously rushing apart is to introduce the idea that there's something there we can't see, either the cold dark matter or this other stuff, which is called dark energy, which is responsible for this motion. Now, if that were a small percent of the material that we needed to make all this happen, it might be an interesting proposal. But the fact of the matter is that actually only like if you divide the universe up by, let's say, mass or energy into ordinary stuff that we can see, atoms, let's say, galaxies, suns, planets, and the rest into this dark energy and dark matter stuff, you end up only being able to account for 4% of the universe in terms of the actual tangible matter that we can observe, the luminous matter. That means 96% of the universe is this cold, dark stuff that can't be observed, which is really, really interesting. So, in other words, the model that we have for all of this expansion business is either 96% wrong or 96% of what's happening can't be seen for some reason. And that's kind of the crisis that cosmology is facing right now, which is really, really fascinating. Again, I always like to say, when you hear the word dark or black or something like that, it's very like death cultish in cosmology. It usually means it's a piece of the puzzle that we haven't solved yet. And I think that's probably the most charitable way to look at it, which is fine because we've been doing modern cosmology for like 75 years, something like that. We wouldn't expect to have everything nailed down today. So, I mean, the other, of course, huge part of the puzzle is that we can't possibly, I personally would think, I don't know how we would possibly expect to understand something like light being redshifted 14 billion light years away if we don't really understand light very well to begin with, right? I've mentioned already today that most physicists think of photons as being this kind of magic blob of stuff that shot off from an atom and never seen of again. But there's actually some really, really intelligent work done on how light is probably better understood as some sort of a handshake between atoms, where the atoms are actually going from one vibrational state to another, and they kind of even out that vibration between each other. Sort of like how heat works, right? We know that heat is not transferred through some magical fluid or magical particle, although people thought that until very recently. We know that heat is just the vibration of one atom getting another one going instead, right? So you have this conservation of motion, and you're basically just transmitting heat because you're transferring the vibrational motion from one atom to the next. The same kind of idea has been applied to light as well, although it wouldn't be the same kind of motion. It would be something else. And there's a guy at Caltech, an emeritus professor I got to know over the years, a fantastic guy named Carver Mead, who really developed that idea called the transactional interpretation of quantum mechanics. He wrote a little book called Collective Electrodynamics, a little tiny green book. You guys, if anybody's interested in stuff, should check it out. It is completely fascinating. But my point being that if we don't understand how light works, it's going to be pretty hard for us to understand what the heck this redshift possibly means, especially when it seems like there's lots of ways to be redshifted that have nothing to do with recession velocity. It seems like a rather enormous leap to conclude that the space itself is expanding as a result of it. How are we doing with this so far, guys? Anybody lost completely and need clarification about anything? All right. All right. So we got to figure out light. Let's see. Do I want to swing back on these galactic mergers? You know, one of the most interesting things about galactic mergers, by the way, I just wanted to show you guys some beautiful pictures of these potential interactions between galaxies, is that if we think that the universe is only 13.8 billion years ago, we don't know whether this is, we can only assume this has only ever happened once, which means that we're not going to be able to see cases where galactic mergers have happened and new galaxies developed, and then maybe they've been through another merger. If that timeline for the beginning of the universe is pushed back further, all of a sudden we have an opportunity to explain these formations and these shapes of these galaxies that might involve multiple different mergers happening. So the real question remains for me whether it's a one-time affair or if it's quite common over trillions of years, and you can end up explaining galaxies as a result of it. Because, you know, there's lots of different types of spiral galaxies, for instance, right? We have the barred versions, we have the ones that seem to kind of the sombrero-looking ones. The galaxy is actually quite diverse in their appearance. And so there's some holes in explaining that as a result of it. Some more mergers. Very beautiful. What's kind of cool too is in these mergers, like in this one we're looking at right now, you actually get these huge, massive blue stars that seem to be dominant in these merging galaxies, which would kind of indicate that you're actually seeing the combining of all, like the birth of all of these really big stars all of a sudden as a result of it. And it might be mergers of stars, it might be gases getting stirred up, getting compressed, condensing, kind of anybody's guess right now. All right, so perhaps another interesting point to lay down on the table as we're kind of building out this cosmology is this interesting finding. This was making a bunch of headlines right when the James Webb went online. And that was that people expected to see, you know, very far, you know, if you look at 13.5 billion light years away, you're only a few 100 million years from the beginning of the universe under the Big Bang cosmology. People thought they would see, all right, we'll get this new telescope and we'll be able to see galaxies forming for the first time. That's what they thought. They figured, well, it's the beginning of the universe. According to this model we built out where galaxies only form once, we should see kind of these, what would you say, baby galaxies or something like that. Something like unformed galaxies or galaxies actually forming for the first time. And to everybody, literally everybody's complete surprise and perhaps horror, what they saw at the beginning of the universe was actually fully formed galaxies that looked more or less the same as the galaxies that aren't too far away from us right now. And so that was really shocking. That's a really interesting piece of the puzzle, I think, which is perhaps driving more and more of a wedge into this birthday business with the 13.8 billion years. And there was a bunch of headlines about this. It was interesting when it first came out. It was so controversial. I actually had one of these astronomers who was, you know, I think at the time he made a headline. He was at University of Texas Austin, and he was like famous because he discovered the oldest galaxy that we'd ever seen, or the oldest star, maybe it was. And he was very confident that, you know, it was probably a calibration problem with the telescope. You know, in other words, it was a new telescope. As soon as we had it sort of set up properly, that this problem would go away. In the intervening, the previous couple of years, it did not go away. In fact, more and more of these were seen, these fully formed, rather mature-looking galaxies at the, very close to the alleged beginning of time. So this is a huge, huge problem. And it hasn't really been solved yet. The only thing people can think is maybe to push back the birthday a little bit further, which of course makes you wonder if every time we get a newer telescope, are we going to just keep pushing the birthday back a few more billions of years? History would say yes, but the jury is still out on that to some extent. All right, so we're going to talk about this cosmological principle a little bit. So you guys maybe recognize this map. This is a map This is from a satellite that actually made a map of what we're going to be talking about, called the cosmic microwave background radiation. And when people generated this map, and we'll talk at length about the CMB here in a little bit, but they were very, very pleased because it seemed like there was this homogeneous source of radiation that was coming from all directions, which really reinforced this cosmological principle that the universe is essentially the same everywhere, right? It's sort of homogeneous and it's isotropic. In other words, it's kind of the same density and thickness. There's the same amount of matter kind of in every direction, no matter where you look. And so this forms kind of the bedrock of a lot of these expansionist ideas about the universe as well, because of course you have to populate the universe with dark matter and dark energy equally over time. Now, I'm gonna really take some time to unpack that, but this map actually, unfortunately, it sort of reminds me a little bit of the black hole image that we talked about before, and I'm going to break this down for you guys later, but this is what the actual data looked like for that WMAP image. What you're actually seeing is differences due to Doppler effects of the motion of the Earth. Of course, the satellite that made that WMAP image is in orbit with the Earth around the sun. So there's a particular motion that comes from it. So there's a lot of data processing and unpacking of that image as it went. And so we'll get into the specifics of how that image was deconvolved and so forth as we go forward. But needless to say, it seems more and more like the universe is not isotropic or homogeneous. In fact, galaxies seem to organize themselves into clusters. The galaxies aren't actually evenly spread throughout the universe from what we can tell. They're actually kind of knitted together into these little bunches, which is, I think, surprising people very much. We can zoom out on those a little bit. And what we find is that not only are they organized into clusters, but the clusters themselves are organized into what look to be like little filaments, right? So you end up with, this is the largest survey of the stars to date. It's called the Sloan Digital Sky Survey. And everybody was kind of shocked when this came out because it seemed like the galaxies were not arranged uniformly throughout the universe, but they actually piled into these superclusters that are kind of strung together on little arcs across the sky, which was really shocking to everybody. Our own group is part of this local supercluster we call the Virgo supercluster. And these things are just unbelievably large. It's very difficult to imagine. So they extend for hundreds of millions of light years in 2 dimensions. And they're 10 to 20 millions of light years thick if you go into the z-axis. It's just unbelievable. The masses of these filaments are something like 10,000 times more massive than the Milky Way galaxy, like these big filaments. I don't know a better word. They're kind of strings of galaxies, which is just extraordinary. So the results of all this work really pointed to this idea that 90% of the galaxies ended up occupying something like 10% of the volume of space that we're looking at. Here's another reconstruction of that kind of filament, right? And of course, the idea is that these filaments have actually evolved over time, in some sense. So originally, the sort of cosmological principle that everything was homogeneous and isotropic, we can still keep that because it's been an evolution away from that idea as things cool. But again, at the end of the day, this whole brick over here that we're looking at when we look at the night sky is supposed to be something like 4 or 5% normal atoms, normal matter, 27% cold dark matter, and 68% dark energy, which is really quite astounding if you think about so little of the tangible, observable matter can be used to explain what we see in the night sky. I don't know. How do you guys feel about that? Any emotional reactions to that? Does it make sense? Does it bother you? All right. You know, um, again, I would point to the fact that in the past, these magical substances like heat, they've always had explanations that have come forth in time. There's been a long battle since the early days of observational philosophy, which evolved into what we call science, of people being on two sides of a debate, and it still persists to this day. There was a philosopher named Comte who originally characterized this as a thing called positivism, which was something like, well, our brains are just insufficient to comprehend the mysteries of nature at some point. And the quantum mechanicists really embraced this positivism at some point. And there was this huge debate at some point between Bohr and Einstein. And this was largely over the wave-particle duality, but some other stuff we don't have time to get into. But basically, Einstein was really, really unhappy with the idea that quantum mechanics was essentially a statistical model of the universe, but it didn't actually have any real explanatory mechanism at the heart of it. In other words, atoms, electrons, protons, they all were essentially able to be described in terms of probability distributions, like whether you're likely to find the electron here or likely to find it there. The quantum mechanicists said that's as far as we'll ever get with it. In other words, that's all that we can ever say. That's the limit of our ability to describe nature, is with this probability. Einstein said, no, I think it just means that we haven't got there yet. And so there was a number of really famous conferences back in Einstein's day, in the 20s and 30s, where there was debates about this. And Einstein ended up, history would say he lost this debate because the quantum mechanicists won out in some sense, that they were correct. Their equations, their statistical equations, did ultimately describe the experiments really, really well. You absolutely can put a wave function on an electron or on a photon and describe how it's going to behave mathematically as the result of these experiments. The only question then becomes whether you think that the universe is fundamentally a statistical equation, or whether you think the statistics describe something that's happening that we can't see at the moment. And I think in some sense, the cosmological debate that's occurring in our era is largely a battle between the realists and the positivists. And this is kind of played out in the philosophical domain too, if you look at the work on consciousness right now. So consciousness, this ability for neuroscientists to be able to explain how we have conscious experiences is actually a huge field of inquiry right now as well. And it seems to be divided into two camps, right? There's these physical realists who say, well, consciousness must be a product of neurons interacting in some way, doing something. In other words, to provide the experiences that we have. Like, how do you explain how somebody knows, the experience? How do you encode the experience of tasting chocolate, for instance, or of falling in love or something like this? These huge metaphysical problems we've talked about in the past. And the physical realists say, well, it's complicated. We haven't figured it out yet, but it's obviously has to have some sort of material basis. The positivists, or the analytic idealists, are kind of like, well, everything that you know is happening inside of your head. And so you can't really ever know things that are happening outside of your head. And therefore, it's not even really worth trying to come up with these hypothetical models of how the atoms are pulling this off, because you don't even know that there are atoms. It just seems like there's atoms. And it can be a real nightmare to interact with these analytic idealists at some point, because they're essentially saying that the world isn't real, that the moon disappears when you look away from it. And at the end of the day, they still get out of the way of the oncoming bus, right? Like, they still sort of act as if the physical reality is there, even though they'll deny it to the ends of the earth. And so it's a little bit of an impenetrable argument. It's a metaphysical divide. It's like, it is a robustly logical conclusion that everything is happening inside of your head. The strange thing is that we can all agree on things that were happening inside of my head and your head. For instance, we're all sitting in a room together. I think we can all agree on that, right? And so it's interesting that at the same time that empirically you can only really say that everything you know is inside of you, we can all agree on things that are happening at the same time. And so the question of whether you're willing to introduce hypothetical explanations for what causes things you can't see still seems to be a little bit out of favor right now, which is really interesting. So I think a lot of these dark energy, dark matter explanations are really of the trend of the positivists and of the analytic idealists who tend to think, well, we're just kind of puny humans, our intellect is limited, and there's probably just pieces of the universe that will never, ever be able to be understood. What's interesting is that people have made that claim in the past. So, I think it was back in the 1800s, there was this huge cholera epidemic going around in England. And nobody knew why everybody was dying from cholera. Cholera is kind of like food poisoning, but really, really gnarly. And there was all of these positivists at the time were doing the same thing that they're doing with quantum mechanics and with cosmological suppositions like dark matter and dark energy. And they were saying, you know what? There probably is something that causes cholera, but the human intellect is insufficient. We can't possibly ever understand everything. Atoms are impossible to see. Whatever's happening is probably small like atoms, and we'll never be able to know it as a result of it. And there's actually, I actually was getting ready for this lecture. I was just reading an actual newspaper headline from London. I think it was from the London Times from this era, and there was actually a quote to that end. It was just like, humans can't, we're not all that we're cracked up to be. We just can't understand some things, right? This is kind of the same thing that it comes down to with this dark matter and dark energy too. It's like, well, you can't see it, but we can't possibly comprehend everything. The universe is strange and so forth. A few years later, of course, there was this, I believe he was a physician, but he was some sort of scientist, and his name is escaping me right now, but he said, guys, he was an advocate of the germ theory, obviously, because he's kind of the winner in this story. And he said, guys, I know you don't think that there's any reason to believe that these germ things are real, but how about you just take the handles off the pumps down by the river where people are pumping their water from? Just take it off so people can't pump their river from the Thames, because the Thames is disgusting. Everybody throws their sewage into it. So how about we just, for a weekend, let's just take the handles off the pumps and see what happens. So they did it. And of course, the cholera went away, right? And so, that was a hypothesis. He couldn't see the germs. He just suspected that they must be there in order to explain the phenomena. Whereas the positivists on the other side of the debate were kind of like, well, it's kind of beyond our comprehension. We just have to live with this cholera stuff. And so I'm kind of trying to cue you guys up for the fact that this problem that I've been really, trying to expose you to is not a new problem. This idea that there's always going to be some arm of the debate that says that things are a little bit beyond our comprehension as human beings. Our brains are limited, our perception's limited, our senses are limited, therefore we can't grasp it. That's always been a threat, and it is dominating very much today, although it's under threat from unusual locations. Extra institutional locations, people coming up with really good arguments who aren't even part of the academy. They're not even necessarily professors, and they're putting up very strong realist arguments for how all these phenomena can occur. So that's the world that we're facing today with all this cosmology. A lot of things aren't adding up. People are challenging it. If we look back over the history of astronomy, pretty much everything always tends to be bigger and either farther or closer than we thought it was for a very long time. Things tend to be way older than we thought they were. Back in the 19th century, people thought that the Earth was only a matter of thousands of years old, which is really crazy. Of course, the archaeologists digging up these dinosaur bones and so forth, and everything that the geologists produced in the intervening years really overturned that. Things tend to be more complex than we imagined them to be. Remember the Cephids? Originally, they thought the Cephids were all one type of star. They ended up being two different types of Cephids, and the size of the galaxy doubled overnight as a result of that realization. And then finally, of course, whenever we see dark or black, it usually means that it's a placeholder for something we just don't understand yet. So, you know, the point of this class is not to tell you what to think, but hopefully to show you how to think about things a little bit better. And ultimately, I think it's really healthy that we all go out and look at these really weird, mysterious, spooky things and try to think about them from different angles and compare those ideas with one another. Because the alternative is kind of just taking somebody's word for it, which, well, that's really scary if you have a whole society full of people who are willing to take whatever dictator or idiot's idea as true. Then we end up in all sorts of madnesses that have unfolded over the 20th century. So I think we are ready to look at the CMB next time. And yeah, we only have 2 classes left, guys. So work on your final projects. Let me know if you have questions, how that's going. And get your missing assignments in. Please don't fail this class. Yeah, as well. No, there will be no class on the final. In fact, your projects are due before the finals week, so you don't even have to worry about them during the rest of your tests. Everything's due then too. Like you have one last little like exit video that you have to do for like a 2-minute video the last week. It's very, very simple. But all of your assignments should be in before finals so that I can start grading them. I will close out missing assignments will become zeros and you will have no way back. So don't fail the class. Please don't fail the class. Otherwise, yeah, guys, have a great weekend and I'll see you on Tuesday.